Hi, and welcome to today's lesson on Pythagorean identities. We reviewed yesterday some of the basic identities you were familiar with from grade 11, the quotient identity being one of them, and the Pythagorean identity being another. Now, to this point, you're only aware of one Pythagorean identity, but we're actually going to introduce you to a couple of others today. And to start off, we're actually going to develop all three just so you can kind of get a sense of where all of them came from. So what you can see right now on the screen is just sort of a review of a few formulas you're familiar with that will actually allow us to develop the one Pythagorean identity that you do know. All right. So for an angle in standard position, we've seen in the past that sine of theta is equal to y over r, cos of theta is equal to x over r, and tangent of theta is equal to y over x. And we also know that the Pythagorean theorem holds for that relationship. Now, looking below, so if we actually start with the Pythagorean theorem, what we can actually do with that expression to sort of convert that into what is now known as the Pythagorean identity, we can actually divide, as it says here, both sides by r squared. Okay, so what we'll end up getting when we do that is an expression that looks like what you see here. So x squared over r squared plus y squared over r squared equals r squared over r squared. Now, the right side of that specifically, r squared over itself, that should just be equal to 1. So I'm going to be able to simplify the right side. Now, on the left side, what we can kind of picture is, well, if I have x squared over r squared, for instance, I could just as easily write that as x over r all squared, because that the squared part would actually apply to both the numerator and the denominator. So now we should recognize that x over r, we've seen already from above, that is just equal to cos of theta, and y over r is actually just equal to sine of theta. So what we end up getting is the Pythagorean identity you would recognize at this point, cos squared theta plus sine squared theta equals 1. Okay, now you've seen that identity represented in terms of different variables, so whether it's theta or whether it's x, the idea that if I'm squaring cosine of a specific angle and squaring sine of a specific angle, adding them together, I always get 1. That's a constant. Right? Now, as I'd mentioned a few minutes ago, there are in fact two other identities that relate to Pythagorean theorem, and we can actually derive both of those in a similar way. So we're just going to quickly look at the development of the two other representations of Pythagorean identities. Okay, so starting with case 1, essentially we're going to start from the same point, the Pythagorean identity that you already know, but we're going to do something different to start with. Now, before we decided to divide both sides by r squared, here we're going to actually divide both sides by x squared instead. So what we'll notice, first thing we'll get is our equation, so from Pythagorean theorem looking like this. So now I've got x squared over x squared. That will be equal to 1, but it's going to leave me with y squared over x squared and r squared over x squared. So you're going to have to simplify those two expressions. So what we'll now have, similar to what we saw on the other side, so now I've got 1 plus, and now I can represent y over x all squared and r over x all squared. Now I should recognize y over x, hopefully from before, that is just tangent of theta. Now the other expression here, r over x, I have to think about that one for a second. That's actually a reciprocal. Normally we see r in the denominator, but the fact that it's x and r, you should be thinking, well, that is actually secant theta. So as it turns out, we're going to get 1 plus tangent squared theta is equal to secant squared theta. So that is actually a second Pythagorean identity that we can now work with. And then lastly, case number 2, similar to the last case, only now sort of the third option we haven't explored yet is, well, what if we divide both sides of Pythagorean theorem by y squared? So what we would get to start with, x squared over y squared plus y squared over y squared plus r squared over y squared. Well, the y squared over itself will simplify to 1. So then it's a matter of, okay, well, what do I do with the other two expressions? So it's going to become x over y all squared plus 1 equals r over y all squared. Now x over y, we've seen before just a moment ago, in fact, that y over x was tangent of theta, so it should actually be the reciprocal of tangent, which is in fact cotangent theta. And then similarly, r over y, we've seen before y over r, that's just sine of theta, so this is going to have to be the reciprocal of that. Now the reciprocal of sine of theta is actually cosecant theta. So what we'll end up getting here, as it turns out, cotangent squared theta plus 1 equals cosecant squared theta. So that is a third Pythagorean identity. So there's a total of 3. In fact, in grade 11 you were only aware of 1, but now we've got 3 at our disposal. As far as just general tips for proving identities, you kind of saw something similar to this in the lesson posted yesterday, and there's going to be a handout that you could look at that sort of lists these suggestions as well. And again, these are guidelines. You're not going to find that the same process works every time, but these are at least some things to sort of keep in mind. So normally simplify one side at a time, maybe trying the more complicated side first. Generally, we want to express all of our relationships either in terms of sine or cosine if possible. Leaving them in terms of the reciprocal identities normally isn't the best approach. Algebraically, if we can simplify anything, that's usually a good idea. So sometimes you can factor, for instance, or if there are rational expressions, maybe combining them by getting a common denominator. And then now that we actually are aware of all 3 Pythagorean identities, if you see either a sine squared, a cos squared, or a tangent squared x, chances are you could do something with the Pythagorean identities if it will in fact simplify the expression you have. Okay, so just some things to keep in mind. Okay, so now we're going to look at some examples just to sort of tie in the knowledge of these new Pythagorean identities for today. So the first one, we have a fairly complex looking expression, at least on the left side. So what we'll do, we're going to split it up into its left and right side to start with. So left side will be tangent squared x plus cos squared x plus 1 over cosecant squared x. There's my left side. My right side is just secant squared x. So my left side, I'm going to have tangent squared x plus cos squared x. Now I see 1 over cosecant squared x, and I think, well, cosecant is the reciprocal of sine. So if I'm actually doing 1 over cosecant, that should actually be equal to, as it turns out, just sine squared x. So I'm going to be able to do that substitution for that third expression there. And then what I would now hopefully pick up on is the fact that I have a combination of sine squared x plus cos squared x. This is actually one of the Pythagorean identities. I should recognize that that particular Pythagorean identity is just equal to 1. So what I'll have now is that my left side is tangent squared x plus 1. Alright, and at this point we've now actually seen a few minutes ago that tangent squared x plus 1 is actually equal to secant squared x. Right, and if I compare my left side and my right side at this point, we now see the left side equals right side, and we'll end with QED. That was what we expected to be proven. Alright, so that example is done. Alright, example 2. So now we have another identity that we're being asked to prove. This one will again just split up to start with the left and the right side. Now here, as far as what we might want to do, I would maybe start with the left side here just because it is somewhat complicated looking. So what we'll do here, one thing to point out, we just saw this in the last example, tangent squared x plus 1, we should recognize that as being a relationship. We should have something to substitute for. In fact, it should be equal to secant squared x. So I'm going to make that substitution right off the bat. So we're now going to have secant squared x over tangent x. Alright, so I'm going to rewrite basically the expression that we see here in a slightly different way, just because I want to kind of picture the fact that I have tangent x in the denominator. I'm going to sort of work towards replacing that with something else here. Okay, so we're going to have sine x plus cos x. I haven't changed my first set of brackets yet, but now I'm going to recognize the next part as, well, this is the same as secant squared x times 1 over tangent x. I'm actually just splitting that rational expression kind of into two pieces, picturing it now more as a multiplication than anything. So now what we'll do, my left side, I've got sine of x plus cos of x. Still haven't dealt with that bracket yet, but we will be getting to that momentarily. So now what I'm going to do is sort of twofold. I'm actually going to replace the secant squared x with something in terms of cosine or sine, since the first set of brackets is in terms of that. So in fact, 1 over secant squared x should be the same as 1 over cos squared x. And if I'm looking at tangent, 1 over tangent, that is actually the same as saying, well, that's the reciprocal of tangent, which is cotangent, and hopefully I would recognize that as just being actually cos of x over sine of x, right? Now the reason that will be helpful is I see, if I'm multiplying these two things together, inside the set of brackets right here, right, if I do numerator times numerator, I would just end up with cos of x. In my denominator, I'm going to have cos squared x times sine of x. Now, the numerator and the denominator happen to have a common factor. They happen to have cos of x in common, so I'm able to divide out any common factors. So what I'm going to picture is the cos of x from the numerator will now have divided out, and I will just be left with a 1 cos of x as part of the denominator that's there. So to sort of tidy this up a little bit, we're now going to have sine of x plus cos of x. All of that will now be multiplying 1 over cos of x sine of x. Right? And just to sort of put all of that together, I will now have, so picture the top, which is just a 1. If I multiply the sine of x and the cos of x by 1, I still have sine of x plus cos of x, but now the denominator is cos of x sine of x. Right? At this point on the left side, there's not a lot else that we could do, simply because there aren't any other identities that really jump out at us. The top, unfortunately, is not sine squared x plus cos squared x, because if that was the case, the top would simplify to 1. But unfortunately, that's not what we have. So we're going to kind of leave the left side temporarily, and then now focus on the left side. So I'm going to compare the left side to what we had on the right side. Now the right side, I'm going to write it over again just so we can see it. Now one thing that would be a good idea at this point is to compare the left side and the right side. Now the left side is a single rational expression whose denominator is actually the product of cos of x and sine of x. So I look at the right side and say, okay, those are two rational expressions. If I was going to add them, I would need a common denominator. As it turns out, the common denominator is exactly what we would have, or what we have on the left side. So it's actually the product of cos of x and sine of x. So what I'm going to do is actually create equivalent expressions on the right side that have the desired common denominator here. So picture, what would I need to do to the first expression in order to produce the denominator that I want? Well, I'd have to multiply top and bottom by sine of x. So that first term will end up being sine of x over cos of x sine of x. And then similarly, I'd have to multiply the next expression, top and bottom, by cos of x. So this will become cos of x over cos of x sine of x. Right? At this point, now that the denominators match, I would be able to add the numerators. And notice what I get when I do that. Sine of x plus cos of x over cos of x sine of x. And if I revisit what my left side was equal to just a moment ago, if I scroll up, that is exactly what the left side was equal to. So what I'd now have, my left side equals my right side, as we expected to be able to prove. Third example, no, we have not done one like this yet. This is a little bit different in that now we're actually considering an identity that has more than one variable involved. Alright, so there's actually a couple of different approaches we could take to proving this particular identity. I'm going to use one approach and then likely follow up with this question tomorrow using an alternative method that will be equally as valid. So what we'll do, like we would normally, we're going to split this up into its left side and its right side. Picking between left and right side, which is the more complicated, I think that it's safe to say the left side is more complicated. Now, one thing we have to be very careful of when we're working with an identity like this is to keep track of the variables. We don't want to make substitutions and simplify things that won't simplify if the variables don't actually match. Again, there are a couple of different ways we could go about doing this. One thing that might jump out at you with this particular question is what you actually see on the right side compared to the left side. What I would focus on here is the fact that I actually see a cosecant squared y on the right side and a sine squared x on the right side. So what I'd probably want to try and do is get the left side in terms of those expressions. Now, what we can do here, as it turns out, we're basically going to try and pick something on the left side to do a substitution for. So we have a few different options here as far as what we could do. Now, one option might be to say, alright, well, I don't see a cos squared x on the right side, so maybe do a substitution for this. And thinking of what we could actually substitute that for, well, cos squared x, I can think Pythagorean identities and say, well, 1 minus sine squared x should be equal to that. So we're going to go left side equals, so my sine squared x cotangent squared y plus, and now picture 1 minus sine squared x in place of my cos squared x, and then times cosecant squared y. So now my left side will equal sine squared x cotangent squared y, and then I'm actually going to expand through my brackets here. So I'm going to have plus cosecant squared y, which is good because I expect one of those should appear on my left side at some point, but now I have to subtract sine squared x cosecant squared y. Right? What I would do at this point is sort of look at, okay, I've got three expressions here, and I'm going to highlight two of them. Specifically, my first expression here and my last expression here both have sine squared x as a common factor. So what I'm going to do here is actually group those terms together so I can actually remove that common factor. So now what we'll do, we'll factor out sine squared x and be left with, okay, I'm going to have a cotangent squared y and then minus my cosecant squared y. Alright, and then I still have the plus cosecant squared y at the end. So what I now need to sort of focus on here is, what was the right side supposed to equal? So it's supposed to equal cosecant squared y minus sine squared x. So what you might be thinking is here, these are almost at the right point because I do have my cosecant squared y, which is being added, and I have this factor of sine squared x here as well, but I'm supposed to be subtracting this. So what you might be thinking is, should that not be equal to negative 1? Okay, if it does, we should have the left side equaling the right side. So it's now really just a matter of showing, that that expression inside the brackets is actually equal to -1. Now, as far as what I could do here to sort of prove that what's in the brackets there's got to equal -1, I have to think of a substitution that we could do. Now, knowing the Pythagorean identities that we now have to work with, one thing we could recognize is that the expression right here, so the cosecant squared y, that is actually supposed to be equal to cotangent squared y plus 1. So what I'm going to do is make a replacement of cosecant squared y within the brackets, and then see what's left over. So what we'll have here, so my left side will now be sine squared x, and now I'm going to have cotangent squared y minus, now the one thing to be very careful of here, I'm subtracting what will now be the equivalent of a polynomial. So I've got cotangent squared y plus 1, and then I do have the plus cosecant squared y still at the end. So now I've got left side equal to sine squared x times, so if I drop the brackets inside here, so picture minus, I'm going to have to subtract cotangent squared y and subtract 1 when I drop the brackets. Now I have plus cosecant squared y. And what I'm able to do inside the brackets here, cotangent squared y minus itself, those two terms are actually going to essentially eliminate each other. So I'm actually going to be just doing sine squared x times -1, and I have to add to that cosecant squared y. So another way of writing that would be cosecant squared y minus sine squared x. And if we go all the way back to what we started with at the top, you'll notice that was exactly what the right side was supposed to equal. So we've now arrived at the left side equaling the right side, so we're actually finished the question. Now, I'd mentioned at the beginning there are a variety of different approaches you could take to actually making this identity work. So what we might do in class tomorrow is explore some other possible ways of working this out. What we did here, though, is one valid approach. Okay. If there are any questions you have about any of the examples in this lesson, just make sure you ask in class tomorrow, and have a good day. See you tomorrow.